Hello and welcome everyone. In this video, I will talk about LLMs, fundamentals of LLMs in simple terms so that even a beginner can understand them. I will not use any of the fancy jargon stuff that you read on the internet. So I will explain it in my own words of how I understand LLMs. So let's start. So what is an LLM first? So LLM, as the name suggests, it's a large language model uh, which is trained on massive amounts of text and which predicts the next token. So basically, this is an LLM. Then we come to training versus inference and parameters and weights. So what I'm about to tell you will cover all these things. So what happens is we have scraped websites, numerous websites. We have collected articles. We have scraped books, like every text on the internet, and we have uh, gathered it together, and we have taken a chunk out of it. So it's almost 10 trillions. Suppose let's say 10 trillion size. And then the AI labs, what they do is they procure thousands of GPUs, the H100s or the other high VRAM GPUs, and they run the simulation, the neural network algorithms on it for number of days, suppose 12 days. It costs them millions of dollars for doing this. And after that is complete, uh, sort of zip file is generated, but it's not really a zip file, since a compressed zip file, since the zip file is a lossless compression, and what this generates is a lossy compression. So sort of everything mixed together. So these are called weights, and they are like billions of numbers. So these are called weights and as well as parameters. So suppose a model is of let's say 24B. So B means it has 24 billion parameters. It is trained on 24 billion parameters. And for each parameters, so this is outputted in a 16-bit format, so 2 bytes. So a 24 billion parameter model would be 24 times 2, 48 GB. So it would take 48 GBs of RAM to run the model. And right, so this is training stage. So what outputs in the training stage is the base model. So base model uh, is nothing but collection of neural networks that predicts the next token. So we can't really chat with it. We can't like give it instructions, and it really can't follow instructions. So for it to follow instructions, we have to fine tune it. So for fine tuning, there is an instruction tuning happens, and after that, then only we can uh, interact with it, like get the user instructions, like converse with it basically. So that is called an inference. We are using the model to get the output. Okay. The next is how language becomes math. So this is very important of how the LLM works. So whatever we input to the LLM, it is English generally. It is plain English in like alphabets, letters, words. But the LLM is a machine. It can't understand language it as well, such as English. It understands only machine language. So what do we do to convert text to machine? There is a concept known as tokenizer. So what is a tokenizer? Basically, it just converts the text into um, token IDs, basically, and those token IDs then are embedded. Now we go to the embeddings. So what are embeddings? Embeddings is nothing but vector representation of text. So once those words are converted to vectors, they are sort of um, placed inside a vector space. So the words are converted to floating point integers, and those integers, if they are semantically uh, similar, they are grouped together inside the vector space. Suppose um, we have cat, and cat jumps on the tree. So since cat and tree are somewhat similar, they will be grouped together at a particular place inside the vector space. So whenever it's a time to generate an output, so suppose if we ask the model, where does the cat jump? So it will predict that uh, what's the highest probability of the next token. So so in that cluster it will have tree, building, some other words, other vectors. So what the highest probability vector would be? The word tree. So it will pick that token and then it will output that token. So that's how it works. So as I was saying earlier, the semantic space. So the vector representation of the text we type. So it is grouped together semantically. Similar vectors are grouped together inside the vector space. So suppose boy, girl, and pizza. So boy and girl will be closer because they are humans, and pizza will be somewhere away from them. So that's how it's represented inside the vector space. Then comes attention. So attention is a layer inside the LLM. It is the ability that uh, describes which previous token is most relevant to the current token. And it is again stored in query key value as a vector inside the vector space. So it 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 helps in picking the next uh, token. So this one decides the probability, which is the most relevant token. So suppose let's take an example. I gave pizza to Rahul because he is hungry. So who is he? To answer that, it will go in the attention layer and it will determine that which is the most relevant token here. Who is he? So he will be Rahul in this case because Rahul is hungry. So I gave him the pizza. And right, so this is how it works. Then comes the concept of KV cache. So KV cache stores the how do I explain this? So whatever text we type in the context window, so the context window gets stored as tokens as text, but KV cache gets converted to vectors. So it converts the incoming tokens to vectors, and it then stores these vectors inside the RAM, so that whenever there is next vector to be next token to be processed, it does not go to the beginning of the token to recompute it. So let's take an example here. Let's say we have inputted token 1, token 2, token 3. In the context window there are three tokens, 1, 2, 3. So KV cache converts these into the vectors and store them in the memory. So when the token 4 comes, it it does not it does not again recomputes token 1, token 2, token 3, just the token 4, because three tokens are already in the memory. It references them, and then it stores it in the memory. So that's why you would see that long conversations generally take it increases RAM more, because whenever the context window gets larger and larger, your RAM increases, and the RAM increases because the KV cache is increasing. So generally, it is better to start a new chat instead of keep on dragging the existing chat and conversation and making it bigger. So why it exists, I already talked about. What it stores, I said. Then context window, I discussed it as well earlier. So context window is the ability of an LLM, like how far back it can see the context or tokens. So suppose there is a context window of 128,000. So it only can refer back 128,000 tokens. Anything beyond that, it forgets. So recent advancements, there has become like 1 million tokens. So it's quite a lot of context window. So right, the context versus KV cache I already discussed. So context is text based, KV cache is vector based, which is stored inside the memory. Then GGUF and model formats. So GGUF, it is a file format which stores the model. So the model itself, by itself, it can't be executed. To execute it, there is a file format which is the GGUF generally. So there is a community of in the Hugging Face which collaborates and contributes to these models. So this is a file format, GGUF. Then it has some metadata, like how much parameters it has, how much quantization it has. I'll talk about quantization later. So, and then the inference engine. So the file format by itself is cannot execute the model, cannot we can't interact with it. So for that we need an inference engine, and that inference engine generally there are quite like two or three. So one I can name is llama.cpp, and the other one is LM Studio. So currently I have been working with llama.cpp. So for llama.cpp to work, first we have to get the source code. Then we have to make the make file, like cmake, and then build. So it prepares the build, and then we build the files. It after build, it checks the configuration, like which compiler our system has. So since I have a MacBook, it has a Clang compiler, and after checking the configuration, it generates the build files. So build files contains like llama CLI, llama server. So all these build files are generated, which helps in inference. Once we load the model inside the memory, we can then use it to interact with it. So when we type something, hello, how are you? So then it starts processing. Then we can actually use the model. Now comes quantization, as I said this word earlier. So what is quantization? So quantization is like reduction in weight precision. So as I said, the weights are nothing but billions and billions of numbers. But when a model is released, unquantized model, 16-bit, so it has like high precision number values, and it's very accurate. But suppose it has a 200 billion parameter model, so it has high precision weights, but not everyone can run these 200 billion models, parameter models. So what the community do is they quantize the model. So what it is that it reduces the precision of the weights. It so what precision reducing precision does is it reduces the uh, space occupied. So it saves the space, but the trade-off is that it becomes faster. It saves space, but the accuracy is less. So there is always a trade-off. So to if you want a lower weight model, so and you will get faster inference, faster token per second, but the accuracy will be slightly decreased. So what is this Q4, Q5, Q6, Q8? So generally we have these four types of quantization. For Q8, so original is 16-bit, as I said. So 16-bit is 2 bytes. So 100 billion parameter model would take 200 GB of space in the RAM if someone has it. Then 8 bits is 1 byte, so 100 billion would take 100 GBs. Then uh, suppose Q4. So Q4 would be 4 bits, so zero point 0.5 bytes. So 100 billion would come down to 50 GBs, 50 GBs. So this is like quantization. This is what it is. So as I said earlier, memory versus quality, there is a trade-off. If memory is high, quality will be like it would respond slow, but accuracy will be high. Then comes the inference pipeline. So what happens when we type something and hit send, like you all do in your chat GPT and Claudes? So whatever you type and hit send, what happens after that? So what happens is the text is converted first to tokens, then the tokens are converted to vectors and gets embedded. They get embedded into a vector space, and then in the vector space, it is processed in the attention layer, and after the attention layer, it helps predict the choose the which is the most relevant previous token for the current token, and after that the next token is predicted. So that's all it is. The LLM is just a prediction model. It does not see text. It does not see like this is a boy or this is a girl. It just works on numbers. That's it. And prediction. It runs on predictability basically. Then base versus instruct models. This is I also discussed earlier. So whenever the training completes, a base model gets outputted. But base model, it's just a token prediction model, so it can't be used for you following user instructions. Like ChatGPT and Claude, they have user instructions like a chatbot, but instruct models, so instruction tuning we have to do on the base model so that we can use it for following the user's instruction. We can chat with it, we can help translate stuff, we can ask for any advice, and you know how to use. Now, decoding model names. So you might have seen somewhere in social media that people talk about uh, Quen 3, 8B, Instruct, Q4, KM, GGUF. So what it is? So let's decode this first. So first is Quen 3. So this generally is the model name. So this is the Quen series 3 model. So somewhere you will see Mistral, somewhere you will see DeepSeek, somewhere you will see Gemma, which is currently released by Google. Then comes hyphen 8B. So 8B is the weights, as I discussed, parameters, uh, 8 billions, and then the fine tuning, which fine tuning this model has. So it has instruct, which means we can reason, we can like chat with it, it will follow user instructions. Then comes Q4. So this Q4 is, as I discussed earlier, this is a quantization, 4-bit quantization. So it would be, so original is 8 billion, so 8 times zero point 0.5 bytes would be 4. So 4, so it would take 4 GB of space in the RAM to load this model. And finally, GGUF, as I said earlier, it's the file format of this model. So simple. Then memory and performance. So weights, KV cache, and TPS. So the bigger the model, the more the weights, the more the KV cache, but the TPS will be low since it has a lot of reasoning to do. It has a lot of uh, prediction to run inside it. So it would be less, the TPS would be less. But if you want high TPS, high token per second, like what you see in your chat GPT, when it's like type outputting all the words, text, those are tokens per second. So, and that is quite high. So you can imagine how much uh, trade-off they have done, the chat GPT and Claude people. So to get higher TPS, the weights would be lower, and also the KV cache would be lower in this case. So this is just my project. I was building Jarvis, local AI assistant, voice-based AI assistant. Let's see how it goes. Okay, thank you. That was all. Hope you learned something from this. Hope uh, it would help you in your understanding of LLMs and for future use. Thank you.